Alright, in this video we're going to talk about gears and gear ratios and their properties. So starting off with gears, pulleys, and sprockets, gears are mechanisms that are used to transfer energy through rotary motion. They can change the speed of a rotation, they can change the direction of a rotation, they can even change the amount of torque that you have available to do work. A gear train is a mechanism that's used for transmitting that rotary motion and torque through interlocking teeth. Most everybody should know that. You know that the gears have teeth around them and they can interlock together. When you spin one, it'll spin the other one. A gear train is made when two or more gears are meshed together. And a driver gear is what's going to cause that motion, and then the motion is going to be transferred to that driven gear. Some facts about gears and their properties. If you have a mating gear and they mate together, they're always going to turn in opposite directions. You can see this on the top right animation here. You also have things that are called idler gears that would go between two gears that are interlocking together, and it would cause those motions to be in the same direction. You can see that in the bottom right animation here. We've got that idler gear in the middle so that our two gears on the outside can spin in the same direction. All an idler gear is going to do is just reverse that direction. If you have mating gears that are mated together, they're going to have the same size teeth. We call that the diametric pitch. And then the RPM of the larger gear is always going to be slower than the RPM of a smaller gear. If we have gears locked together on the same shaft, they're always going to spin in the same direction and the same RPM. Okay, so you can see that by this animation here. We've got a larger gear that's going to be spinning slower than that smaller gear. And the gear, the blue gear and the yellow gear are on the same shaft, so notice they're spinning in the same direction at the same RPM. Going into gear ratios next. There's a couple different variables we're going to have to define to find gear ratios, but you'll find out that the calculations and stuff are very simple. So first off, we've got a lowercase n. That's going to stand for the number of teeth on a gear. We've got a lowercase d. That's going to be the diameter of the gear. We've got the omega symbol, which looks like a small w. It's going to be the angular velocity or speed of the gear. And then we've got the tau symbol, which looks like a small t, and it's going to represent torque. Okay. We also use subscripts when we're dealing with these symbols. That way we can tell what is the input gear and what's the output gear. Okay. So for these two gears on the top right here, you'll see we've got a larger blue gear that's moving 20 RPMs, and then we've got the number of teeth on that gear is 12 teeth around. You'll see the diameter is 4 inches. Then you'll see that the angular velocity is again 20 RPM. You'll see that the torque is 80 feet per pound. For the smaller gear, you'll see that's the smaller red gear. The number of teeth it has is 6 teeth. It's got a diameter of 2 inches, and the speed of it is going to be 40 RPMs going counterclockwise. To find the gear ratios, which is just the mechanical advantage of that gear, there's a string of formulas that we can use. I would suggest writing this down in your notes, that way you can have it. So we know that a gear ratio over 1 is going to equal one of these different variations in the formula. Okay, so the way that this works is as long as you have two parts of this. So if I have the number of teeth out and the number of teeth in, I can find the gear ratio. Okay, or if I have the diameter of both, I can find the ratio. Or if I have the speed of both, I can find the ratio. Okay, you just need to make sure that you have both components. Okay, so you might be given a problem on a test or so that where you're given both number of teeth, but you're only given one diameter. Well, you can't use the diameter to figure out the mechanical advantage there because you're only given the diameter of one of the gears. Where you could use the teeth, however, because you were given both teeth. Okay, so we're going to set our gear ratio. We're going to try to find our gear ratio and put it over 1. And we're going to set all these equal to all these different components. Okay, so you'll see number of teeth out over number of teeth in. Well, we know that's 12 over 6 based on our image up here. Our diameter out over our diameter in, that's 4 over 2, again, based on that image, so on and so forth. Okay, you can set these equal to each other. Okay, so if I wanted to use number of teeth out, for example, I could set my gear ratio over 1 equals number of teeth out, 12 over 6. Okay, do my algebra to figure out what the gear ratio is missing, what gear ratio is missing there. Okay, so we're going to do the same thing for a couple problems here. What is the gear ratio between the gear A and B? Okay, so you'll see A is this larger blue one with 20 teeth. B is the smaller green one with 12 teeth. Okay, so we're given number of teeth here. So we're going to use the number of teeth variation right here. So we'll set it equal to our gear ratio over 1. Do that math out, it's going to equal 12 over 20. If we do that, divide that out, it'll give us a ratio of 0.6 over 1. What's the gear ratio between gear B and C? Again, we're going to use our number of teeth to calculate this. So number of teeth out over number of teeth in. So 5 over 12 gives us a gear ratio of 0.42 to 1. Again, gear ratio between C and D. Again, we're going to use number of teeth. 20 is going to be our output teeth because that large gear is being driven by the small gear with 5 teeth. And that's going to equal to be 4 to 1. What is the total gear ratio? Okay, the way we figure this out is similar to how we did mechanical advantage in the previous slides. All you have to do is multiply all of them together. So we found all the individual mating gear ratios. Now we're going to multiply them all together. The total gear ratio would be 1 to 1. If we were to connect A and D directly together, what would the resulting gear ratio be? Again, number of teeth out over number of teeth in, 20 over 20. That's also going to give us 1 to 1. What would the total gear ratio be if the last gear had 40 teeth? Work that out. 40 teeth over 20 would be 2 to 1. Now we've got compound gear trains. And you'll see we've got an animation here where we've got gears that are on the same axle together. Okay, so in this instance it's hard to tell because it's a 2D image, but that green gear is driving the yellow gear. That blue gear is on the same axle as the yellow gear. And that blue gear is driving the red gear. Okay, so those two middle gears are going to share that common axle, so remember they're going to share the same speed and the same direction. Okay, this is going to allow that final gear to rotate slower and produce more torque than if we were connected only to the driver gear in this instance. So finding the gear ratios here, what's the gear ratio between A and B? Okay, again, we're going to use our number of teeth out. Number of teeth out is 40 in this instance. Number of teeth in is 10. Put that over each other. Gear ratio of 4 over 1. And then what is the gear ratio between C and D? Again, that's going to be 50 over 20, or 2.5 to 1. What's going to be the gear ratio for the entire train? Multiply those together, and we'll have a gear ratio of 10 over 1.